continuing on with section 3.5, we would like to look at price elasticity of demand. Demand is a massive force in economics. You really need to know what policies affect the demand, and one way in which economists measure the responsiveness of consumers to change in price of a product is with price elasticity of demand. So, is it elastic? Is it not elastic? Is it inelastic? Neutral? For example, a drop in the price of fresh tomatoes might result in a much greater demand for fresh tomatoes. Now remember, you don't need fresh tomatoes to survive. So these are commodities that are not a must for you to just continue your daily life or to cook, or you could survive without them. Apples the same deal, grapes the same deal. Those are not a must. Such a demand is called elastic. That is, if you drop the price and the demand goes up, we call that elastic. But if you drop the price or higher the price and the demand doesn't get affected as much, those are inelastic. On the other hand, the demand for items such as they found out that coffee, smoking cigarettes, price of the gallon are relatively unresponsive to change in price. If they go up a bit or down a bit, you're still going to drive to work. You're still going to take the trips that you take. You will still drink your coffee. If we increase the price of a coffee cup from $1 to $1.75, people will still drink it. Whoever drinks coffee doesn't stop. Cigarettes went up almost 100%, actually 100%, almost 1,000%. They went up from roughly less than $1 to almost $10. People still smoke. So certain habits are hard to really, and it doesn't mean if you lower the price people will smoke more, but this is kind of what we're trying to really study out of this. How does demand get affected if we play with the price of an item? If it does get affected, sales go up, the demand goes up, we say that's elastic. If the change doesn't really occur, we say that's inelastic. The demand for such items is called inelastic. That means no matter what, we're going to spend this much on of course, the pandemic changed. We're not talking about exceptions. If we had our daily routines, and, I teach 5 days at this school. I'll drive to the school. Let's say it's 20 miles away. I drive to the school and back. If the price of the gallon of gas goes up or down a bit, that's not going to change much demand. I'm going to drive the same amount every day. If the gallon goes cheaper, that doesn't mean I'm going to drive more. Of course, there are a few exceptions, but I'm talking about the economy as a whole doesn't get affected much. So, if it does get affected, we say that's elastic. If it doesn't get affected, we say that's inelastic. And this is how we find it. This will be provided on your test. You don't need to memorize that table. It says, if P is f of x, this is a function that you can take a derivative of, then the price elasticity of demand is given by this formula, where this by the way, this is the letter eta, Greek. This is the price. X is the number of units. Right? Did they say that anywhere? No, they don't. Okay, we'll say that. Number of units. And this is the derivative of the price function with respect to x. When eta is the lowercase Greek letter. For a given price, the demand is elastic if the absolute value of this quantity right here is bigger than 1. It's inelastic if the absolute value is less than 1. And it is unit elastic if it equals to 1. So we say it's elastic if the revenue goes up it's inelastic if the revenue goes down, and we say it's unit elastic right there. So this is an upside down parabola. I'm going to show you how to graph that really quick without using a graphing calculator, because they're going to use a graphing calculator. And I summarized those for you right here. So it's basically this formula. It is you figuring out this eta, that is p divided by x over dp dx. I need a value for that, and let's see how that works. So if I look at this, number 28, demand function and quantity. So if I find the price of elasticity of demand for the demand function at the indicated x value, is the demand elastic, inelastic, or unit elastic at the indicated value, at one value. Use a graphing utility. I'm going to graph this by hand. I'll show you how to graph it by hand. For the revenue function, and identify the intervals where you have elasticity and inelasticity. Well, let's see how that works. If I am to proceed, so to figure out this eta, I will take P. Well, P is 400 minus 3x. That's the price, that's the unit, that's the demand function, divided by x, all over dp dx. The derivative of this with respect to x would be negative 3. Right? So this is actually, I have a calculator, and they say the first thing they want, find the price elasticity of demand for the demand function at the indicated value of x. This value of x. So if I take this and I replace x equal to 20, I will get this eta to be 400 minus 3 times 20 over 20 divided by a negative 3. And I could put that in my calculator one shot. I could take parentheses, 400 minus 3 times 20 divided by 20. I could hit equal and divide that by a negative 3. Well, that'll be a negative 5.6666. Or, what was it? 17/3. Negative. In absolute value, that's bigger than 1. And if it's bigger than 1, we agreed that's elastic. We have an elastic demand, which means if you increase the price, the demand will go up, and vice versa. So this does get affected. Now, let me show you how to sketch a quick graph. It's not going to be exact, but without a calculator, this is the best we could do. So it says, use a graphing utility, this part, to graph the revenue. Isn't the revenue function x times p? Isn't that x? And what's p? Isn't that 400 minus 3x? Very simple to graph if we're just mimicking the graph of a specific parabola. If I was to say, where does this equal 0? Wouldn't you say when x equals 0? And when x equal, if you solve that, isn't that 400 over 3? Half of that if you multiply this by a half, that's 200 over 3. That's the peak. So this is an upside down parabola, y equal x squared. That looks like this. It's symmetric. And guess what? This is the revenue. This is x, number of units. And isn't this going up? So when they say identify the intervals of elasticity and inelasticity, we say elastic from 0 to 200 over 3 and inelastic from 200 over 3 to 400 over 3. Does that always work? Yes, that always works. How about problem number 30? If I want to figure out EDA, I need the demand function, the price, which is 15 minus 0.000, how many? 3 zeros over x, all over the derivative of this. Isn't that negative 0.0003? If I evaluate that at 25,000, wouldn't that be, and let's see, get my calculator out, and I'm going to take parentheses 15 minus 0.0003 times 25,000 divided by x. X is 25,000. Again, I could put the whole thing one shot. Divided by a negative 0.0003. All one shot. I'll get it to be a negative 1. In absolute value, that's 1. So we say this is a unit elastic. Unit elasticity. We say this is unit elastic. And if I want to do part B, the second part, it says sketch the graph of the revenue. I'll say, well, revenue is x times p, right? X times, and what's the demand function? And if I was to sketch a graph of that, okay, you know what? Here we go. We're always talking about positive. If I set this equal to 0, that will be 0 right there. And where would this equal 0? I'll get my calculator out and I'll take x equal, if you solve this, 15 divided by 0.0003. 50,000. Half of that is, this is symmetric always, is 25,000. And again, I'm just giving you a rough graph. And if this is the revenue and this would be the units, well, what do we know? From 0 all the way to 2500, we have elastic. Zero to 25, not 2500, I mean 25,000. And it's inelastic from 25,000 to 50,000. And that would be it. And let me do one more. The demand function for a product is modeled by this. X is between 0 and 200, okay? Where P is the price per unit in dollars and X is the number of units. Very good. A, determine whether the demand is elastic or inelastic. Oh, and of unit elastic. Well, let's see. Tau is P 800 minus 4x divided by x all over So it's p over x over dp dx over the derivative of this. The derivative of this is a negative 4. If I play with this, well, this is going to equal 800 minus 4x over x. Instead of dividing by a negative 4, I'm going to multiply by the conjugate, meaning it is going to be 800 minus 4x over 4 times 1 over negative 4, or simply getting carried away there. That's going to be 800 minus 4x over negative 4x. If I put an absolute value on it and I split that up, wouldn't that be 800 over negative 4x minus 1? Or wouldn't you say that's the absolute value of negative? And what's that? That's a plus 1. I'm sorry. Negative over a negative. 800 over 4. Isn't that 200? So let's see how this works. If I have a limitation on this between 0 and 200. Well, if I want a 1 out of this, if I want to get a 1 out of this, or here, even better. Oh, I love it when it does that. Okay. If I want to get a 1 out of this, if I want this to equal 1, now think about it. This is negative. Don't I want this to be a negative 2? Negative 2 plus 1 is a negative 1. Absolute value of that of 1 would be 1. That would mean that I want to get a 2 out of that. I want x to be 100. If I want this error to be an absolute value, if I want that to be bigger than 1, again think about it. 100 and negative 200 over 100 plus 1 is negative 2 plus 1 is negative 1 absolute value. If I made this x smaller, if I let x be between 0 and 100, let's say I let x equal 50, negative 200 over 50 plus 1, isn't that negative 4 plus 1, which is 3? Isn't that bigger than 1? And if I want this to be less than 1, just have x be between 100 and 200. Now, this will be unit, elastic. Here, since it's bigger, that's elastic. And inelastic. So common sense. And this is part A. If I look at part B, that's going to make things a bit simpler, I think. Use the result from part A to describe the behavior of the revenue. Again, look at the revenue. Isn't the revenue function x times p? Isn't that x times 800 minus 4x? And if I really look at this graph, and again, this graph will give away. I was tempted to do part B first, then go to part A. Think about it. This is 0 at 0. And if I set that equal to 0, 800 divided by 4 is 200. Not a coincidence, you guys. And halfway through, and let me tell you, that's how parabolas look like. Those are always symmetric. This is 100. 100 is really the unit elastic. And from 0 to 100, do you see that this is elastic? And from 100 to 200, do you see that this is inelastic? So I could have done this and went backwards, and that would have made things a lot simpler. So this graph is easy to do provided it's a parabola, and it's always the case. And here's the rest of the homework. Even though we only have 3 problems, extremely important to figure out and understand.